So the final presentation of this session, Dr. Mojtaba Mahmoodian from RMIT University, and his topic is digital twin development for intelligent monitoring and maintenance of concrete structures.
Okay, good afternoon, everyone. Very happy to be among structural health monitoring experts from different places of the country. My presentation is not that technical. I just mention what we are doing in our project. How do I change this? You change it for me? Or? Oh, yes. Okay, so digital twin is a concept we hear these days maybe a lot, is a favorite topic. But what we mean in our project about digital twin, I'm going to explain. These are some general information about the significance of, let's say, structural health monitoring, why we need to look after bridges. Unfortunately, with all the traditional methods for inspection we are doing, and as well as instrumenting bridges with sensors and looking at that sensor data, trying to translate sensor data to understand the structural integrity of bridges. But sometimes we hear in the news that there is a bridge somewhere in the world collapses and has its consequences, which is obviously not good. Visual inspection or even non-destructive testing have this high cost, risk, or limit of accessibility, as the previous presenter mentioned. So, and might be very costly and might be prone to bias or prone to human error. So these are the challenges for, let's say, traditional way of structural health monitoring or visual inspection. Then the solution or potential solution as digital twin, as you know, more recently advanced term for civil infrastructure, is coming from aerospace engineering, and where actually they have a much richer or more technically rigorous somehow field. So around 1969, they started to develop this concept of digital twin to create a digital model of a physical structure which is live. So whatever happens to physical structure, you can see the reflection in the digital model. So this is what we call digital twin. So there should be obviously a connection between the physical structure, in our case bridge, and our digital model to call this a digital twin. So what we wanted to do in our project was to instrument our bridge with sensors. Sensors wirelessly send data to our digital model. Our digital model is actually a finite element model. Okay, but now is live, is not offline finite element model. So it's real time. So imagine a truck or a vehicle passing over the bridge. In our digital twin, in our FEM, we can see change in the color, for example, which shows the stress concentration under the vehicle wheels. Okay. And with that, we expect to see any stress concentration or increase in the displacement, any structural problem which might exist or any defect on the bridge, we can catch and we can detect in our digital twin, digital model. So that was the purpose. So we can call this a real-time finite element model. And we actually, for this development, we needed to integrate different technology. So obviously Internet of Things, because we deal with wireless sensors and how these sensors communicate to each other, how they shoot data to our data logger and then receive data remotely. This is the first part of the technology. Then finite element modeling by itself is another piece of the technology we needed to develop. You know, for a bridge, a reinforced concrete bridge, which are our case studies. So an offline finite element model by itself is very computationally expensive and takes long time for a complete model to run. So. Now we want to make this FEM real time. So we want every second, let's say, this model run. So that make it very challenging to have such a big model run, even with the supercomputer exists. So that's other piece of technology need to be developed. Then we wanted our digital twin be intelligent as well, not just to show the output of a real-time FEM, also can decide for us or can predict future. So imagine 5 years this digital twin working, creating real-time FEM. Thank you very much. So we collect 5 years of history of structural performance of a structure. Then we thought, okay, let's see if we can predict future, next 5 years, what happens to the structure. If in future somewhere of the structure gonna experience damage or failure, so use machine learning techniques or what-if scenarios as well to predict future. So that makes our digital twin intelligent, not just give us real-time or current data or current understanding of the structural integrity of the bridge. Also, we can predict future. So that is where artificial intelligence could help us. And then also to make it user-friendly, using some visualization technique to actually make the output of this digital twin more user-friendly. So 2 case studies we had in our project, which is, I will explain about our partners. So we had 2 reinforced concrete bridges, one in Victoria, one in New South Wales. This is Boronia Bridge in Victoria. We started with the small bridges actually because we wanted to make sure the technology we are developing actually meet the objectives and can respond, then maybe go for landmark bridges or more critical bridges. So we started for a bridge with actually one span bridge. These are the dimension, and if you see the cross section is like a reinforced concrete with U-shape cross section, and started with creating its offline finite element model and looking at the different mode shapes. And then we needed, obviously, to validate our FEM model. So we went to the field, used some accelerometer to actually install and check the natural frequency, compare with what our finite element model giving us, and find this and validate our FEM model. So this is the field test we did. So we obviously needed to arrange traffic management to direct the traffic to the middle, have our vibrometers 2 sides of the road, and collecting data, and then finding natural frequency, and then check with our model. Then when we were confident that our model is validated, then used some optimum sensor placement methods to find optimum sensor places. So normally, sensors are placed where actually you see maximum, for example, these are strain gauges. We decided to put strain gauges where you experience maximum strain, for example. But here, because the purpose is to actually have minimum number of sensors, which actually are cost effective, and also the sensor data are reliable enough to make our finite element model reliable and actually catch every potential local, even local defect. So we tried different methods and tried to develop existing method to actually reach to that point. And this is the second bridge in New South Wales. So, so in terms of where we are standing about the progress, we are in the actually process of purchasing sensors from supplier. I explained the challenges we had about the sensors as well. And then installation going to be done in a couple of months. The other bridge, just to get you an idea about the other bridge in New South Wales is Bunurang Bridge. This is how it looked like, a bit of dimension. There is a river passing under. It's an I-beam bridge in terms of number of beams. More beams here, a bit bigger than the first one. And here we are planning to actually equip this bridge with fiber optic sensors. Okay, for the first one, Boronia Bridge in Victoria, we are using wireless sensors, but for this one, we thought we experience another type of sensors to be installed to actually experience as researchers how they might work differently to find constant crowds of each. So these are finite element modeling again for that Bunurang Bridge in New South Wales. And again, field work to validate our FEM, finite element model. And yes, again, we had to direct the traffic to the middle, put the vibrometers in the side, and collect natural frequency, and then check with the numerical model result to come up with the to find out if our model is validated or we need to do some changes. So that's about validation. Again, sensor placement, where to put sensor, what type of sensors. These are the challenges. So that's maybe overall methodology. It's important how to design the architecture of your digital twin, how these data are collected, how they actually set on your digital platform. So here you can see overall view of this. So data collected, FEM is created. And then you're gonna have this FEM real time, how you're gonna overcome that challenge of finite element running for a long time. So you need to make it actually quick. So using reduced order modeling, for example, or other technique can help with this. And then adding an algorithm, AI algorithm at the end for real time, for remaining useful life prediction. So yes, if I want to list the challenges we had, so sensor type is always challenged. There are suppliers in Australia and internationally. Each claim they have the best sensor with 10 years battery life, but when you go for real use of the sensors, you realize, okay, yes, battery life might be 10 years, but if you want your sensor send you data every second, the battery life is only 1 year maybe. So then all those benefit of this bridge instrumentation that you talk, okay, we're gonna eliminate the need of annual visual inspection and reduce the cost for the asset owner, then asset owner might come back to you and say, okay, if I want to change every year, I have to change the battery, then this is costly for us. So your system is not cost efficient. So these are things need to consider. Then if you think about, okay, instead of battery, sensors with battery, let's use solar panel. Then where install the solar panel? Then what do you do with vandalism? if we had this experience with one of the bridges. So sensor we installed were broken by people easily a few weeks after installation. So these are things to consider. And digital platform also important. So what platform you're gonna use, AWS or using smaller platform provider. So because it is important, you're gonna receive data, sensor data every second from sensors. You're gonna have huge data after 1 or 2 years. So where are you gonna store this data? So for your digital twin, you need a digital platform because you realize it has several pieces. You have sensor data used as input to your FEM. So you need somewhere that your FEM software or code working, and then creating output to save output somewhere, and then use your Python algorithm or machine learning for prediction. So all of these pieces of digital twin need a digital platform. So what we are planning to use in our project is RMIT AWS. We have a good capability here at RMIT to use that platform as well. So these are challenges I just wanted to share with you. If you have experienced same thing or you have a solution for this, more than happy to discuss. And in terms of how digital twin might help with sustainability, so we believe that digital twin can help with better monitoring and maintenance of infrastructure, and by prolonging lifetime of civil infrastructure, in our case, bridges, for example, we can actually have our asset for longer time and then save money and resources for future generation. That's mainly how it actually, I think, helped with sustainability. And the alignment with those UN sustainability goals, goal 9, 12, and 13, I think are those main goals that are target for digital twin development. I would like to thank all our partners. This is actually a part of a big project I just presented today, where RMIT and 3 other universities are collaborating together. We have 10 industry partners and who are helping us to develop this technology. And we think this is applicable for other civil infrastructure as well, rail infrastructure, pipelines, tunnels, and so on and so forth, and even buildings. Thank you all. This is a list of my colleagues helping me with this research, and thanks for your attention.
Thanks, Mojtaba, for your presentation. And you've got a pretty bold vision to create a real-time finite element model. So it'll be very interesting to see how you get to there. But any questions? I'll go from this side this time. I'll come to you next. Second.
How much time for?
How much time was taken to install the sensors on those particular bridges?
So for that validation, we actually did this in a day or half a day, let's say, because those were there temporarily, just to collect vibration data. And then we took sensor with us and then did the rest of job on the desk. So that is like temporarily you put there for every, let's say, 2-3 minutes, collect data, and then check if data is okay, then we are fine. But normally it takes several iterations. And but yeah, when for our digital twin, that was for validation of our FEM. For our digital twin, we're gonna leave the sensors permanently on the structure because we want our FEM continuously receive data and be real-time FEM.
When you're modeling this structure and looking at this structure in real time, and you see a truck is running on the bridge, and at the same time you're doing the analysis on your computer, right?
Yeah.
So how do you know what load is running on the bridge?
We actually only receive sensor data. So from the load effect, which are sensor readings, actually we're gonna calculate back the load for our FEM model.
So you're back calculating.
Yes, is an inverse FEM, actually.
All right. And the second one is you're doing linear analysis, I assume, because you're doing real time, should be very quick.
Is non-linear. Yeah.
So it's non-linear for concrete.
Yes, yeah. To be more accurate, yeah. But
Such a quick time.
yeah. As I said, we use techniques to make it quick, yeah, so.
Yeah. Yeah, because obviously it should be non-linear, because if you are in linear stage, the bridge is safe.
Yeah.
The bridge has problem when it goes to non-linear.
Exactly. Yeah, it's non-linear analysis, but yeah, we sort that problem with the time, yeah. That might need another presentation to go to that technical.
Final question for the session.
Yeah, just on the non-linear thing, I was just wondering that because the non-linear analysis usually takes quite a bit of time. It's quite computationally expensive. How I might have missed it. How are you actually doing that? And is it just like, are you just pumping it with a lot of clusters or something like that on the cloud, or how are you running that non-linear analysis in every second and solving it every second? Because it does take a while, the Newton-Raphson thing, it's like pinging all over the place. It does take a while for it to converge usually.
Yes. Just as a short answer, we use AI. Okay.
Okay.
We use AI. We train our FEM, so our FEM is sort of intelligent. Now.
Right. So it's a hybrid.
We run it offline.
Yeah.
We make it trained and be intelligent. Now, when it's on real time, using those algorithms we generated, make it very fast.
So it's not just so I'm clear, because I really like the idea. So it's not pure finite element. It's a hybrid between AI and finite elements.
Exactly.
Okay. All right. Beautiful.
All right. Thank you very much. I think that's it for this afternoon. And please feel free to ask more questions at the networking session. But thank you very much for your presentation, and be very keen to find out where you land in a few years' time.